Section 4.4 title is Direct Proof and Counterexample, Division into Cases, and the Quotient Remainder Theorem. In this section, we will be basically focusing on the quotient remainder theorem. Here's a quick outline, and we will talk about the quotient remainder theorem first. We'll quickly define what the word modulo means. We're not really going to get into a whole lot of depth there. And then finally, we're going to talk about the method of proof by division into cases. Start with the theorem 4.4.1, quotient remainder theorem. Basically says, given any integer n and a positive integer d that we call the divisor, there exists integers q and r such that n is equal to dq plus r. R is known as the remainder, q is known as the quotient. The special thing about the quotient remainder theorem is that there's a guarantee if we divide n by d that the remainder is either 0 or some integer smaller than d, the divisor. For instance, if n is 11 and d is 4 and I divided 11 by 4, then I'm going to end up with a quotient of 2 and a remainder of 3. This is because 11 is the divisor 4 times the quotient 2 plus the remainder 3. The guarantee is that the remainder right here is a number that is between 0, possibly equal to 0, and the divisor, in this case is 4. Here are the examples. So think about what would happen if you divided 54 by 4, for instance, in example number 1. What would your quotient be, and what would your remainder be? Well, in this case, the quotient is going to be 13, and the remainder is going to be 2. And again, the guarantee is that the number 2 is some number, some integer, that is greater than or equal to 0, but at the same time less than the divisor 4. You divided by 4, so the remainder is guaranteed to be either 0, 1, 2, or 3. It cannot be anything else. Because if it were anything else, that means your division was incorrect, that means your quotient would have been wrong, and you would have to perform the division one more time. This even works when your n is negative values. So in this case, example number 2, n is negative 54, and the divisor is 4. So what would happen if I divided negative 54 by 4? Keep in mind, I'm always searching for a remainder that is a positive value. In my case, negative 54 turns out to be 4 times negative 14 plus the remainder, which is 2 in this case. So again, it is a coincidence that the remainder here and in the first problem were the same. They don't have to be the same. The special thing about the remainders is it's a number that is greater than or equal to 0, but at the same time less than the divisor. In this case, it's 4. Now, there are instances when the divisor is larger than your n. That's what's going on in example number 3. N is 54, and the divisor is 70. So what would happen if you divided 54 by 70? Well, it's not going to work. 54 does not contain inside of it 70. It's smaller than 70. So the quotient is going to be 0, and the remainder is 54. Now keep in mind, the remainder is a number that is between 0, possibly equal to 0, and the divisor. In this case, the divisor was 70, so 54 is a number between 0 and 70, so it still works. The theorem still holds. This is an important theorem, so it's a good idea to try to memorize what the statement of the theorem is. So generally speaking, n is equal to d times q plus the remainder r, and the special thing about this is the following. The divisor is typically speaking an integer, so it could be positive or negative, but we don't really care about it so much. The quotient and the remainder are both integers, and typically speaking, we don't know what the quotient is and we don't really care, but we like to focus on the remainder, and the remainder is guaranteed to be something that is greater or equal to 0, but at the same time less than the divisor. So that is probably the most important part of the whole theorem for what we want to be doing in this section. Now, what does the word modulo mean? What is the definition of modulo? Modulo basically refers to the remainder that you get when you divide by d. And the special thing here is that the remainder has to be, again, some random number that is greater or equal to 0, but less than the divisor. So for instance, from the previous slide, we had 54 divided by 4 and the remainder was 2. So we say that 54 modulo 4 is equal to 2, meaning 2 is the remainder that you would get if you divided 54 by 4. Similarly, 2 again is the remainder when you divide negative 54 by 4, because 2 is the remainder you would end up with when you use your quotient remainder theorem. Then finally again, 54 divided by 70 is 54, which means that 54 is the remainder. So we say that 54 modulo 70 is equal to 54. So 54 is the remainder when I divide 54 by 70.